Howdy, physics sleuths and inquisitive souls. Welcome to Dynamic Gravity. Um, this episode, I think we're going to dig into some of the math of dynamic gravity and see if we can't figure out kind of what's going on here. The math that I've created for this, I'm not entirely happy with because it succumbs to the same problems of Newton's law and Einstein's law, which is that basically there's kind of like different levels and scales on how gravity seems to operate. Like we have the level of on this planet, things dropping things, and then we have the level of like moons orbiting planets, and then we have the level of planets orbiting suns or stars, and then we have the level of stars orbiting galactic centers, and then we have the level of clusters of galaxies orbiting each other. um, and it seems that every time, not every time, the first three levels, things seem to hold together pretty well enough. But as you start getting into the galactic level of the stars orbiting the cores of the celestial or the galaxy, um, things just kind of fall apart. And I'll show you what I'm talking about. I wasn't fully aware of the problem of this until after I did this math and saw it, and then looked into it. And yep, that's a problem. That it's the way it goes for all theories of gravity. So you know, Newton's law of gravity is pretty good. We use it. We can use it to calculate plotting a satellite around the orbit of like Pluto if we want. That's how accurate it is. It's very accurate. It's essentially 100% until you start getting to elements like time dilation and extreme like black holes or something. Then Einstein seems to work a little better because it includes that. So, Newton's math works fantastic in our solar system, but when we get out of our solar system, it kind of falls apart. And so this is, what we calculate, but this is what we actually see. And so it just doesn't work. So then people created modified Newtonian dynamics, MOND, which is basically just tweaking Newton's formula to get the proper. I think here's the latest one right here to get the proper answers to fit the observations, and this does work. This works. You can make this work on a galactic level. So you can say, well, for whatever reason that we don't understand, gravity changes its fall off rate after a certain distance or size or whatever. And things get changed. And I just had a loss of thought here. So yeah, they tweak the formula, and this is what they got. And you can see it's pretty close, they just basically have it like square rooted it instead of having an r squared. Now it's just an r fall off rate, and then the square root of the mass times the gravitational constant times the modifier, which is supposed to tell you how gravity is going to behave at that particular distance or whatnot. And doing that, we can completely mostly completely attribute all the observations we see on gravity in the galaxy. But then once we start going to galaxy clusters, it all falls apart again, and it doesn't work. It's changed. Gravity has changed yet again. And now my theory of gravity, dynamic gravity, is based upon the displacement of the electromagnetic force. Go back, watch the original videos I made about this if you have any confusion. I don't have time to go into it right now. But something interesting. Coulomb's law explains the electromagnetic force, between the proton and the electron. Like you can calculate the force, just like you can calculate the force between two celestial bodies, using Newton's theory. Now look at this. Look at this. Gravitational constant times the mass times mass divided by r squared. We have K, the Coulomb constant, times the strength of the charge of particle 1 and the strength of the charge of particle 2 divided by r squared. It's almost an identical formula. The exact same mechanisms that's going on. This is telling you between the force between two planets is identical to what is happening in the atom between the proton and the electron, or two protons or two electrons. That's what this formula is telling you. We know it works. This is legit. So this is just more proof that I'm right and Einstein is wrong, that gravity does behave from ultimately the electromagnetic force. Just think about that for a second. The exact same style equation that we use to describe gravity works for the electromagnetic force. They also conveniently have the exact same fall-off rate. Of all the fundamental forces, the electromagnetic force is the only one that has the exact same fall-off force as gravity. So, I mean, that's compelling evidence that, the two are related, just like I say they are. But no one else has quite figured that out yet. So, now, the math. Let's, let me switch this up here to this. There we go. Okay, the math. Here are formulas. Here's the formulas that I have used. Here's the Newton's formula right here. Here is the Coulomb's formula that I have used. Only instead of using the strength of the charge of the proton or electron was designed to calculate, I'm instead using the strength of gravity of the celestial body, otherwise known as, gravitational acceleration. So like for the Earth, that will be 9.807. So, calculating that, then what we get is a number that we times that number by Newton's force, and then that will give us, according to this math that I've created, it gives us all of the amount of anti-gravity that's working on the objects. Because you gotta remember how gravity works and dynamic gravity. We got two objects like the Earth and the moon, and the moon is orbiting the Earth. But according to Newton or Einstein, they're going to tell you there's zero repulsive gravity keeping that celestial body at bay at the distance. They're going to say the only thing that's acting to take it further away is centripetal force as it's rotating or revolving or whatever. I say no. Two celestial objects that are large enough are going to exert a repulsive force. And that's the reason why we don't really observe celestial bodies ever colliding, throughout the universe as far as we can tell. Super celestials, there's, some exceptions. That's why they're always the exception. But for the most part, we don't see evidence of celestial bodies like two, a planet and a moon just crashing into each other. I think the only moon that has any sub damage is like Mimas or whatever. It got hit by a really large object, definitely much larger than like a comet or an asteroid, but it wasn't like large enough to be another moon. So there's just no evidence that it happened. So for that to happen, there has to be repulsive force. So that's what we're calculating with this formula. And then we compare the two to see the repulsive force will subtract from the pulling force. Newton's traditional force is what we're calculating. And then that will give us the actual gravity force that's interacting between the two celestial bodies at that range. So let's just do a little math here. This, I just did it just to check it, see how it would come out, as if it was like an object. You'd want it to be negligible. You would want, let's take away formula. There we go. Here's also the formulas written mostly in their entirety, stacked up. It's kind of a long series of things. Yeah, this also tells me the optimal distance, like when the repulsive force of gravity starts to win out and become dominant over the pulling force. That's what I designed this formula to tell me, assuming everything works. So we calculated. We have an object on the Earth, 9.807, and there's the weight of the Earth, right? And then the weight of this object is just like 2 kilograms, very, very small. And the radius is just like 1 kilometer, whatever that would be. And then we have the gravitational accelerational field that this object is going to be creating. So it's just like a ball, a kilogram ball or whatever. It's going to be minute. It's going to be negligent. It's going to be almost completely zero. And when we do that, this is our Newton's gravity that's calculated, and here is the total gravity is calculated. You can see they're not quite the same, but they're almost identical. I mean, you have to go down to like I don't know, 1,000th or 1,000,000th of a percentile before you start seeing differences. So that's just something, and I just kind of guessed as to exactly how strong the gravitational field of said ball would be. But okay, let's do some math now. I'll show you why. When I first made this theory, I was so hopeful. When I first made this math, I was so hopeful it would work. Right? So let's take this and do the moon. Right? I got everything listed here, all the data, so I can go back. I calculated, a lot of stuff here, just to see how things would work out. So we got the Earth and 9.8. We got the moon. The mass is there. The distance is 384. So we are going to put that distance there. And the moon's gravitational acceleration is 1.62. Okay, 1.62. Now, these are the numbers that you get. All right, you get 0.966. So if I take 0.966, which is almost essentially 1, and I times it by Newton, what Newton gets right here, and then I subtract that from Newton to get the actual force, what you get is, I wrote it down here too, 6.67 e to the positive 24th. So that's still a lot of force, but you have to remember the original number was to the 26th. So this is essentially like 1% of the force that was acting on it through Newton's calculation, which would mean that the force between the Earth and the moon are in stasis. They're in equilibrium, where the moon is just far enough away that its two gravitational forces, pulling and pushing, are being canceled out and almost nullified. And now, of course, the moon is on an elliptical orbit, so this is, I think, the average. As it gets further away, that repulsive gravitational force will diminish, and then it'll be more pulling force, which will kind of act to pull it closer back into equilibrium, the point of equilibrium. And then as it gets an elliptical, as it gets closer to the Earth's orbit, it's going to be the repulsive gravity force is going to be winning out, and that's going to be pushing on the moon, saying, no, you're too close to me right now, get back to equilibrium. And this is a beautiful way to explain why the universe looks the way it does. And it does explain a lot. The problem is this works out great when we're talking about, I thought I calculated all of these, but it looks like I didn't. But anyways, the gravitational forces that we get when we calculate all the moons, right? Like Io, Europa, Ganymede, Mimas, Encephalides, Dionon, Triton, Titania, Oberon, all of them. All the moons, it works out really good. There's only a couple of moons that are in complete equilibrium, like our moon is. But our moon is the solo moon, where they, as you can see, have multiple moons going on. That are going to be thrown into the calculations and making it much more muddy and harder to actually get a full calculation of what's going on. You have to calculate everything, acting on everything at that point. So, but it works out pretty good. It comes out to tell you that most of the moons are pretty close to equilibrium. They're not too far away. Some of them are like half, 0.5, some of them are 0.8, but they're all pretty close. They're all really close to equilibrium, which is what you would expect if you're trying to explain observation using this theory of gravity or this math. So that works out great, right? Now, the problem is when we start to calculate the planets, it goes down. It goes down a lot. Instead of them being equilibrium, it's saying that most of the planets are way further away. So there's really not much anti-gravity affecting them. Maybe like some of the planets, depending on what planet it is, will have like 10%, or maybe even as little as 1% going in the case of like Uranus or something. So that doesn't look good. If what you want, if everything is in equilibrium, then your math should say that everything is equivalent to zero when you sum out the balances of the two forces, the anti-gravity and the regular gravity working together. If they're truly in equilibrium, it should sum out to be about zero, kind of like the moon is, our moon, or most of the moons. But that just doesn't happen on the planets. It's still not bad. I mean, 10%, even 1% isn't the worst. But the problem is when we get down to galactic level, like here are two stars acting on each other. And as you can see, the force is negligible. It's not the same. I know it rounded it off to be the same. Yeah, okay, you can see in the top part, but it's like, it's almost identical. It's like a millionth of a percentile or a thousandth of a percentile, that range. And as we get out calculating our sun from the galactic black hole, now it's still not the same, but it's really close. It's once again, it's like 1,000th of a percentile. We calculate two black holes. Our galactic black hole, with Andromeda's black hole. Oh, my bad, you can't see that. Okay, yeah, our black hole with Andromeda's black hole. And what you can see is it works out to be very small anti-gravitational forces working on it, which is what we would basically call dark energy. This is essentially what we're trying to calculate here through this formula. According to my theory of gravity, would be dark energy. So, like I said, you would expect it to be closer to zero, is what you would expect. But that's not what we got. What we have, in fact, is just like maybe 1% or 1,000th of a percent of anti-gravity acting for every component of gravity. And, I'm kind of bummed out by this, but I haven't really tried to finagle the equations much. Like they do Newton's equation in Mond. I could easily do some Mond tricks, and I'm sure I would get, because my formula is so identical to Newton's. It's Coulomb's law essentially for planets. I'm sure that could easily be used to calculate all the motions within the galaxy. But then, as I said earlier, we got the same problem where, okay, when you got, two galaxies orbiting each other, now it goes up even higher, a higher order. And so it just appears that gravity does not work the same at all levels. It seems, for some reason, the further gravity goes away, or the longer the distance that gravity is acting on something, the more that changes. Or another way to think of it that might not be correct, and that's the way Mons think of it, but the way I think of it is when you have objects like black holes, the amount of influence that their gravitational acceleration is, like here, it's 9.8 for Earth. But if we look, the gravitational acceleration for Andromeda's core is estimated, like, what is this, 4 million? Yeah, 4.5 million compared to the Earth is 9.8, or the sun, or the star, or my bad, the moon is like 1.6. I think our sun is like, what was it, like 400 and something? Let me see. Here we go. 274. That's 274 is the gravitational acceleration of our sun. And so, even our black hole is like 3.9 million, strength. And other stars are equivalent more to ours, like 200, 339. Proxima Centauri is 1,400. Barnard star is over 1,000. According to my theory of gravity, there is absolutely the more dense you compact matter, the further out you're going to extend out that gravitational field. So, and that is essentially what you're calculating when you're calculating using Coulomb's law, the GR times the GR. But apparently it changes as it gets to such a higher degree. So I'm going to keep playing around with these formulas. It's probably going to take me a while to make some sort of progress, but if I do, hey, it could be revolutionary. Who knows? And try and do kind of a Mons approach to fix this math, to make it fit the calculator, the observations that we see. Because right now, my math works great on moons. It works terrific on moons or on the planet, But as soon as we start getting to the level of, planets orbiting stars, it starts to fall apart. And by the time we're at stars orbiting stars, or stars orbiting, galactic black holes, it's just as far off as Einstein's or Newton's. Maybe not quite so far off. So I guess there's that, but still, there's problems. So yeah, I thought I would share this with you guys and show you what I've got so far. I'm kind of heartbroken, that when I did the very first calculation of the Earth and the Moon, and it just happened to come up out of all the astronomical values to cancel out to almost zero, exactly what I wanted it to do. Of course, I was very excited. But as I started calculating all the celestial objects, that we know of, at least their gravitational acceleration throughout the entire known universe, I started to see, how the math started to fall apart with those extreme distances or extreme gravities being acted upon it. So I'm gonna do some modifying on this and see if I can't get it to work better or properly, shall I say? But yeah, so this is just one approach, you guys. To try and deal with gravity is just calculate the normal gravity and then try and calculate the amount of anti-gravity, and then subtract the two and see what you actually got working there. And that's that approach. Like I said, if this math would work out perfectly like I want it to, it would totally explain dark energy. Like that's what we're trying to calculate, and it works on moon levels. But all of the levels, it starts to fall apart and not work so much. So anyways, there you go, ladies and gentlemen. Hope you enjoyed this dive into the math, what I have so far. Wish I could have done a better job explaining it to you, but I'm really not the greatest at explaining mathematics and stuff like this. I just, if you feel like, you want to check out the math or do the math equations yourself and see what you get for all these numbers, have at it. Otherwise, hit me up if you have any questions, and have a good day.
Like, subscribe, submit.